Hey everybody, welcome to Chem 12.2. We're going to get started up with our organic chemistry section and start to proceed through all the different outcomes that are within there. So the first thing that we're going to get started up with is hydrocarbons, and what I would encourage you to do throughout the slides, and really all of the slides, is to have some way that you're learning the material as I'm talking about or going through it. The notes are posted up on the website, and you can feel free to copy them in your book. If you feel like you learn better that way, you could have them printed off and make notes in the margins. The biggest thing is kind of being prepared to go through the learning aspect of this. So we're going to start off with the organic chem section. It includes chemistry of almost all carbon compounds, regardless of where they came from, regardless of the origin. There's over 1 million organic compounds, so they're abundant. The simplest compounds contain only carbon and hydrogen, and they're called hydrocarbons, and that's really, as you can tell from the title of the slides, is kind of the main focal point of this lesson. So the two simplest hydrocarbons, they're known as methane and ethane, and hopefully you've heard of those before, or familiar maybe with one of them with something in your life. So we have to have a little bit of prior knowledge here to go through, and it's not a lot, but there is a periodic table that's attached in the handout section here, and we're going to refer to that just kind of throughout. So how many bonding pairs can carbon make? So carbon itself can make 4 bonding pairs. We can see that as we start to go through its 4 valence electrons. So hydrogen, on the other hand, can only make 1. So to make a molecular compound between carbon and hydrogen, we need to make covalent bonds until we have these full outer shells, and that's from our octet rule. So carbon and hydrogen are going to want to make bonds together, basically. So if carbon has these 4 valence electrons around the outside, and I started introducing hydrogens into them, that means that I could actually have 4 potential hydrogens fill in those carbon valence electrons. So because it has those 4 valence electrons, it can always form 4 covalent bonds between them. So if we take a look at methane and ethane, methane is going to have our carbon in the center, and then we have our 4 valence electrons. Now notice here it's CH4, that means that I have 4 atoms of hydrogen. So hydrogen is going to go all the way around to fill the octet rule, and then instead of using the dots there, in previous years I've used X's just to denote it's a different atom. These are the ones that belong to hydrogen. So CH4 would look something like that if I were writing it out, and then if I were to start using these sticks instead, I could just say that I have carbon, and then I've got my 4 hydrogen branching off, kind of understanding or remembering that each one of these lines represents 2 electrons. I would like for you to try ethane before I do it. See, just if you understand it, what you get, and then we'll run through what it looks like here. So again, try it out, pause it, and I'll continue on. So ethane C2h6 has 2 carbons in it and then 6 hydrogens. So I start off with my carbons, and each of those carbons have 4. And then my hydrogens have to start to come in. Well, the middle part is already done for me. So if I just look at the empty electrons, the valence electrons that are looking for pairs, I can see that I'll end up actually having 6 hydrogens going around them. And so if I again label those just different because they're electrons for hydrogen, then what I can see from here is that I have my carbon forming a carbon bond, and I've got hydrogen kind of moving around the outside of my carbons. So altogether I've got this C2H6 structure, I've got ethane. The ability of carbon to form these stable carbon-carbon bonds is one reason that carbon can form so many different types of compounds. So its difference in its ability, as we start to see these like 3D ball and stick models, carbon can form a bond with another carbon atom, as well as hydrogens. It's quite versatile in that sense, because it has these 4 valence electrons. So we're going to start off with this kind of branch known as alkanes, and it's in this section that we really start to really just focus on rules and properties and that kind of stuff, but you're going to notice that the endings become very important. So when I say endings in this case, it's kind of the A and E. That part specifically is kind of for the next little bit, and then we'll start to change those little endings and really just see how they mean something else with the carbon bonds. So methane and ethane, they're examples of alkanes, and an alkane is a hydrocarbon where there is only single covalent bonds. So there's just single lines, or there's no double or triple bonds or anything like that. All carbon-carbon bonds are single bonds, and all other bonds are these carbon-hydrogen bonds. So again, they're single bonds, but they're carbon hydrogens. The carbon atoms in an alkane, they can be arranged in straight chains or in ones that have branches that come off of them. So we're going to take a look a little bit more just to kind of see what that means, and that they can be straight chains or have these branches. So if you have your textbook on page 695, I did take a little screenshot of it, but it would help just for you to go through and just kind of understand what this table is getting at. So table 22.1. So if you want to open up your book just to kind of follow along, you can as well. So we can see that we have the names for each of them, and starts off with methane, ethane, propane, butane, and then really once you start to get into 5 and on, if you look at the prefixes for them, they should start to make a little bit of sense. Hex is 6, hept 7, octate, nona 9, deca 10, just representing how many carbon atoms there are that are present. And then after that, we can kind of see like the structural formulas for them, and we'll talk a little bit more about what those structural formulas kind of represent. But overall, we've got this CH4, C2h6. For propane, it takes 3 carbons, kind of in a straight line, and then 8 hydrogens around it, and so on down the list. The boiling points for them, what you can start to see is the boiling point for methane is quite low because methane's a gas. So as we start to increase in complexity and increase in carbon compounds, you can see that the boiling point to turn it into a gas starts to become a little bit higher. So things like butane are right around 0 degrees, and then once we start to get into pentane, well, it's 36 degrees Celsius before it starts to boil. So as we start to move down further, these things are really liquid at room temperature, and then we need to achieve these high temperatures to kind of change their structure and change them, their state into a gaseous state. So what pattern, hopefully, do you kind of see out of that? That table is just something for you to look at, see if you can notice what's going on here. It'll give you a second just to kind of take a look at it. And so if I take a look at the carbons, they're increasing by 1 every time. If I take a look at the hydrogens, it's starting at 4, but then it's going 6, 8, 10, 12, 14. It's increasing by a set pattern every time. So when this happens, we call these homologous series, if there's this constant change in molecular structures from one compound to the next. And if you can, try to derive even a little formula from this. What could I take the equation for it, the homologous series, and get rid of the numbers and kind of put in a letter to represent what would be there? How do the carbons compare to the hydrogens? So if I had CN, for instance, I would have CH2n plus 2. So whatever carbon number I have, if I double it and add 2, that will tell me how many hydrogens I have out of there, and that's known as a homologous series. So I do have model kits. I encourage you to pause here if you're in class, or come back later and try it out. But I would like for you to try to draw butane first on paper, and then after that we're going to try to also build butane. So it shouldn't take too long, but it does give you kind of an extra perspective on how some of these things are built. So Once it's drawn, you can probably tell, say, how many covalent bonds there are, and how does this connect to the homologous series of alkanes. When you start to build it, take a look at different things. So the question out of this is, why are 3D models a more accurate representation of organic molecules than 2D models? So if you drew it out, and then if you're here and using the model kits, you should be able to see it. You could also Google it as well, Google butane, and take a look and see if what you're building kind of works out to what you're seeing on there, and how that changes a little bit maybe from how you drew it out. So I'm going to leave that there and just see if you can Google what's there, ask questions while you're here, and I'll certainly come around and explain some things. So there's different ways scientists describe different compounds, and if we take a look at table 22.2, it's page 696, we can kind of see that all of these really are talking about butane. They're talking about C4H10. So again, if you want to flip to your textbook to take a look, if this is a little blurry, it'll be clear there. We have the complete structural formula. So complete structural formula breaks everything apart, so you kind of see like an expanded view of it. Then we have the condensed structural formula, and the only difference to get from what we have in here to what we have going through in this one is that each carbon is basically just saying how many hydrogens are surrounding it. So there's 3 hydrogens surrounding that first carbon. Then the next carbon, it only has 2 hydrogens that are connected to it. So that's why it's H2. Next one is H2, and then there's this H3. So basically the CH bonds are kind of understood that they're there. In the next part, we have the condensed structural formula, so the carbon-hydrogen and carbon-carbon bonds are understood, so you don't even need to write the lines in for this next condensed structural part. And then after that, if we keep going further into this and they keep simplifying this as more things are understood and how we write equations out, we can see that any ones that are the same inside the chain are combined together. So we have CH2 and CH2, so that's why there are 2 CH2s. Now, you would think, well, why not 2 CH3s? They're the ends of your chain, so they need to be separated. After that, we can take a look as this keeps going further and this starts to get more into university style of writing things out. They don't even have the hydrogens in the next one. It's a skeleton. So all the carbon-hydrogen bonds are understood, so they're not even present. As soon as we see a carbon in a structure like this, you kind of just think, okay, there's hydrogens that are there. And then the very last one doesn't even have carbons in them. Anytime I have an end of a line or a corner, it's assumed that those are carbon compounds, which then is also assumed that they have hydrogens associated with them. So this little line, this zigzag right here, to a chemist actually means the same thing as seeing this all the way through. So it's kind of neat how far you can come along as the more you start to understand about how this stuff looks. For our purposes, we're going to be sticking kind of into here and here for this course as we get used to just drawing them out and naming everything. So for a little bit of practice, I'd like for you to draw the complete structural formulas for the for the straight chain alkanes that have 3 and 6 carbons in them. So pause the video, give it a try, we'll go through the answer for it. Alright, so if we were to draw the one with 3 carbons, we start there, and then after that we have our hydrogens that go around the outside. It basically makes it so every carbon has 4 different connection points, and I've got hydrogens that surround my carbons. So if I count them out at the end, I've got C3H8. And the last one wants it for 6. Well, that's just the same thing, just a little bit longer. So I start off with my carbons again. And then remember, each carbon has those 4 valence electrons, those 4 covalent bonds to them. So I'm going to have 5 carbon-carbon bonds, and then everything else to make carbon have full octets around the outside to give it that full balanced shell is going to be a hydrogen that's going to add in. So just start adding in hydrogens. And then I have my structural formula for the 3-chain and for the 6-chain. So we are going to move on from here and keep going, but this is kind of enough for the first video to pause from here.